thanks for everyone for coming. It's good to do this at a new user group. I haven't been to Alt.NET before, so this is my first time. It should be good. So for those of you who don't know me, my name's Daniel Chambers. I'm a senior developer at Redify. My Twitter handle's up on the slide, so if you have any comments or feedback or whatever, or questions, feel free to tweet at me there. So before we take a dive into why I think F# is so awesome, we should first take a high-level look at what it is, the sorts of problems we have as developers writing code, and what we can sort of expect F# to help us solve. So firstly, we find it difficult to write code that's composable. I've seen a lot of code in my time that is highly coupled and quite difficult to change. We also find it difficult to write code that's generic and reusable. I'm sure everyone in this room at some point, including myself, has copied and pasted code around the code base and then paid for it later when you have to edit, that one thing that you copied around multiple times to add some enhancement or fix a bug. We do find it difficult to write code that's maintainable and readable. Like, we understand the code perfectly while we're writing it because we've got all that context loaded up into our heads. But the next person who hasn't seen this code before, who has to maintain it, reads it and his brain explodes, right? Or even if we come back after 12 months to look at stuff that we haven't looked at in like those 12 months, we look at it and go, oh, geez, what was I thinking at the time? So it's important that the code we write is as maintainable and as readable as possible for the next bloke as well as for ourselves. We also want to deliver quality software, right? But of course that is often quite difficult to make sure that it is quality to begin with and stays quality through continuous testing. And of course, concurrency. Now these days we've got multiple cores in our phones even, so sometimes the only way you can get additional performance is to start doing things in parallel. But it's not just data processing that benefits from that better approach to concurrent programming. UIs fundamentally have to deal with concurrency. You want your UI thread to keep pumping the message pump to make sure that your UI stays responsive while you're processing work in the background on behalf of your users. So functional programming and its techniques can offer us ways to help solve these problems. So one of the fundamental pieces of functional programming is the ability to treat functions as first-class objects. And what this really means is that we can pass functions around like we pass data around. This allows us to more easily compose together reusable pieces of our programs, where those pieces are functions. Partial application of functions, which is a technique that we will get into a bit in a few slides, helps us write more composable, more reusable, and more readable code. Another strong functional programming technique is the application of function determinism and purity. And so that's kind of a mouthful, so we'll break it down. Function determinism is referring to a function that takes some certain input, and for that input it will always return the same output. So therefore that function acts deterministically. Function purity is referring to a function that has no side effects. So I'm sure everyone here has most of the time works with mutable code and with a lot of shared state, right? So most of the functions, the methods that we write are impure. They modify and have some side effects on some shared state. You probably run into situations where that becomes quite complicated because you've got functions that share that state, and to understand how that function works, you have to understand how all the functions that it shares state with work and what order and how they interact and at what times, and so that can get out of control pretty fast. That's a problem that you don't tend to have when you're working with pure functions. So also when you write pure functions, you'll find that you can make your data structures immutable. This can make your code more easily able to be concurrent, and we'll see examples of that coming up. And when your functions are pure and your data structures are immutable, you'll find that your data structures can obey what's known as value semantics. So the simplest way to explain this is that an identity of an object is not the particular instance of the object in memory, but rather is the value of the object itself. So the string is the typical example of this, right? You can create the same string twice in memory, but when you compare them with equals, they're the same. However, they are different copies in memory. Unlike the classes we typically create, which even though they may have the same values on all their properties, if you do an equals compare, they are different if you haven't otherwise changed that behavior. So value semantics coupled with immutability makes comparing and caching objects absolutely trivial. So functional programming sounds scary, but the truth of it is that we've actually been doing a bit of it for a while now. Lambdas in C# are functions as first-class objects. LINQ and RX are derived from functional programming techniques, as is async. In JavaScript land, we're pretty used to passing around functions, and that's just the way things are done. And in Java, they've got Scala and Clojure, which are both functional programming languages that are enjoying sort of increased popularity these days. And Java itself, late to the party as usual, managed to gain lambdas relatively recently. So now we're going to get to F#. F# is a general purpose functional programming language for .NET. So what this means is that it works with all the .NET libraries that you're used to, as well as libraries that have been written specifically with F# in mind. F# is a statically typed language. The current hipster trend is to kind of hate on static typing because it's too hard and there's too much ceremony and plumbing. But the fact of the matter is static typing instantly prevents an entire class of bugs from being in your code at the press of the button. And that button's the compile button, right? Static typing also allows for better tooling and refactoring support. If you look at big companies that maintain large and complex code bases, they choose statically typed languages. For example, Microsoft, they invented TypeScript, which adds static typing to JavaScript, so that their JavaScript developers could more easily maintain large JavaScript code bases. Facebook invented the language Hack, where they add static typing to PHP because they find it difficult to maintain their very large PHP code base. So by slowly porting that across to Hack, they're able to gain some of those tooling and refactoring and compile support. In addition to this, we should also consider that some of those criticisms of static typing are valid. So what F# does is it supports type inference. And what this means is that when you're writing F#, a lot of the times you don't actually have to state the types that you're using. The compiler will just infer the types for you based on the context of what it is you've written. So F# is also auto-generalizing, and what this means is as it's inferring those types on your behalf, if it sees an opportunity to introduce .NET generics, then it does it automatically, and you don't have to do anything for that. That means automatically your code is more easily reusable across types. F# is also immutable by default, so this encourages you to program using those functional techniques that we touched on before. Because immutability is a feature of the language, it makes it very easy to do, which isn't the case in a language such as C#. So unlike C#, where you've basically just got classes, structs, and delegates, in F# you've got a much richer set of types with which to describe your data and your logic. These different types allow you to write cleaner code because the compiler is able to take care of a lot of the plumbing details around these types of types for you. So obviously F# has functions. It's got something called a record type, which is basically an immutable data structure that has a set of properties. It's got tuples, and tuples are a cheap way of passing around two or more things. It's got discriminated unions, which describe a choice between different things as a data structure. It has something called an active pattern, which allows you to isolate conditional logic out into a single place. And because it's a .NET language, it does have things like classes and structs and all the stuff we're used to in a typical .NET language. So we'll go into detail on what those different types are in future slides, but you should just be aware that they're there as we go forward. So let's first take a look at how we'd start doing some immutability in C#. Here's a class that represents a game. So you'll first see that we've got the four properties. We've got name, developer, year, and a list of platforms. You can see that all of the properties have private setters, and they're only set through the constructor, right? And the list of platforms that we take in is actually taken in and then converted to a read-only collection. So once we create an instance of this particular class, we can't change it at all. It's immutable. So now let's look at how we do the same thing in F#. Straight away, we can see the difference, right? Not only is the code much cleaner, it's much more readable and smaller. So what we can see there is basically how you define a record type in F#. A record type, as I said before, is basically just a set of properties. It's immutable by default, so once you create an instance of a record type, you can't change it. F# will automatically implement iEquatable and iComparable on that type for us, which means that we get that value semantics for free and we didn't have to do anything. In C#, if we wanted the same effect, we'd have to implement those interfaces ourselves. So that would mean overriding get hash code and equals and implementing compare and then maintaining those over time. So if we were to come to that class later and add more properties, we'd have to remember to go update those implementations. Otherwise, we'd end up with bugs in our code. In F#, that's just not a problem because the compiler takes care of it for you. So one of the pain points of immutability is, what do you do when you want to change something? Well, you can't change it because it's immutable, so what you typically do is you copy it, and as you make the copy, you make the change. So this is how we do it in C#. So on that first line, what we're doing is we're creating an instance of a game, Halo 5, and what we're going to do is we're going to modify it and add a platform to the list of platforms. So in that second line, we're basically cloning that list of platforms and adding PC to it, right? Then in the third line, what we're going to do is we're going to recall the game structure, make a new instance, pass in all the old values from the previous instance, with the exception of new platforms, which is going to be that new list of platforms we want. So you can kind of tell it's messy. It's sort of verbose, and it's also difficult to maintain, because you can imagine if we went to add another property to this class later, we'd have to go to all the places where we've done a copy for this particular line, the last line, right? And we'd have to add to that the new properties to make sure we're copying it each time. So that's a maintainability nightmare, right? There's another thing, that constructor, right? Here we can kind of tell the properties we're setting just because of the sorts of things we're setting in there, but some classes take, like, for example, a number of bools or a number of integers, so it's not always clear what it is you're actually setting. So some people prefer to use object initializers there, so you can actually see what it is that you're setting, but we can't do that here because all our properties have private setters, so we can't use that object initializer. So now let's have a look at how we do it in F#. Again, we can see how much cleaner it is. So that first line with the green box around it is basically how we create an instance of a record type. We've got the curly braces, and then in between them we basically list the properties that we're setting and the values. You'll see that we haven't stated the game type anywhere here. F# has inferred the type for us, and it's done that by looking at the properties that we've listed there, and it goes, oh, I know what name, developer, year, and platforms come from. That's from the game type, so it automatically infers the type for us. That square bracket syntax is how you create an F# list. So F# makes it very easy to create lists on the fly, so that's just a list with one item in it. Now, to actually do the copy and the change, what we do is we basically start with a baseline. So we've got game1, so that's our baseline, and we say with, and then we list the properties we want to change. So in this case, we're changing that platforms, and we're adding PC to the existing list of platforms. So we didn't have to list any of the other properties that were getting copied. The compiler takes care of that for us. We only have to list what we want to change, which means that if I want to add another property to that type later, I can do that, and I don't have to go change all the places where I've done a copy and add another constructor parameter. So the other thing to note here, that list there addition, we're doing that using a cons operator, so that's that double colon. What that's doing is basically creating a new list and putting PC at the front of it. So keep in mind that that's not changing the original game1.platforms list. This is copying it. Now, it's not a blind copy like it was in C# when we actually did the copy of the elements. This is going to reuse the memory of game1.platforms because immutability is part of F# and the libraries support that. So where there's efficiency benefits that they can give you, you get them. So we saw a let binding on the previous slide, and you might have assumed that that was a variable declaration, and you could call it that, but you're better off thinking of it as a binding of a name to a value. And the reason for this is because by default, let bindings are immutable. If you try to mutate a let binding, the compiler just rejects you by default. Again, notice a lack of typing here. The compiler has inferred integer for us. So now you've kind of heard me rant for a bit about why and how easy it is to do immutability in F#, but I haven't really given you a good justifiable reason as to why you should actually care about it. So one of the strengths of using immutable data types is that it makes concurrency a lot easier to do. Because if you have immutable state, it's very easy to create race conditions in your code because you have, for example, two threads that are sharing some state, and one will change it before the other one expected it to, and they'll end up tripping over each other. We typically deal with that through locking and synchronization constructs. But for those of you who've done it, you know how complicated that is and how difficult it is to get right and how tiny little edge cases can escape you and they crop up and they're very difficult to reproduce. So we want to try and avoid that if possible, right? So if we have immutability, that whole class of race conditions are immediately eliminated because it's impossible for one thread to change the state of another because everything is immutable. So the example up on the slide is from my work at a client recently. we were writing a code generator in F#, and it was taking 14 seconds to generate a model of the classes that we were going to generate. Now, because we were using immutable records and all our functions were pure, I could literally make a 3-character change to this code and introduce parallel computations to bring the time down from 14 seconds to 6 for free. So all I had to do was switch from using the seek function, so seek is short for sequence, which is basically operating over iNumerable, to pseek, which is parallel seek, so that's basically plink, switching to that, and it brought the time right down for me. Now, I didn't have to think about threading and concurrency and worry about all of that hard stuff because I knew it was impossible for my threads to interfere with each other because my data structures are immutable and my functions are pure. So you were probably squinting at the code in the previous slide, and that's okay because we haven't covered some of that stuff, but we'll get stuck into it now. It's time for us to look at function definitions. So the function definition I put up on the slide is probably one of the simplest ones I can come up with. It's basically an add function, right? So we're saying let add, and then we're listing the parameters A and B. And then what we're doing is we're adding the two together, returning it, and returning the result, right? So we haven't put any types there, so the compiler has inferred it for us. So the type of the function is something that takes an integer, takes another integer, and returns an integer. To invoke a function, all we have to do is use the name and then just list the parameters after it, right? So here we're taking add, invoking it with 2 and 1, and getting back the value of 3. Pretty simple. So one thing you probably noticed there, that there's no curly braces here. Unlike typical C-style languages, we don't denote block scope using curly braces in F#. We use white space indenting. So that's a bit weird for those of you, and probably most people who are used to C-style braces, but you get used to it very quickly, and then it becomes preferable very quickly as well. So if we think about it, the smallest definition of a function is something that takes one input and returns one output. In F#, functions are curried, and what this means is that the compiler automatically reduces functions to their smallest definition, taking one input and returning one output. So now if we take a look at that weird type signature that you saw before and probably raised an eyebrow at, it starts to make a little bit more sense because the add function is a function that takes two things. So the F# compiler will reduce it to that smallest definition, a function that takes one thing, which is the first integer, and returns one thing, which is a function that takes the second integer and then returns the result, right? So what this allows us to do is do something called partial application of functions. And what that means is that we can basically invoke a function and not pass all the parameters to the function right then and there. So the example up on the slide, we're basically taking the add function and we're only passing the first parameter to it. When we do that, we get back a function that takes the remaining parameters. In this case, just that second integer, right? So we've built an increment function. We've taken that add function, we've partially applied 1 to it, and we've got back a function that takes an integer and adds 1 to it and returns the result, right? So these partially applied functions can be used just like any other function in F#. They're no different. So, for example, we're using it here to increment 2 to the value of 3. So we can also define operators as functions. So one very important operator in F# is the forward pipe operator. And that's what it looks like. It's obviously defined in the libraries. You don't need to write it yourself, but this is just for instructive purposes, right? So it's the pipe and the greater than symbol. Now, the pipeline operator is a binary operator. So that means it takes two parameters, something on the left and something on the right of the operator. So in this case, arg is on the left and func is on the right. And what this operator does is it takes the function that you pass on the right and invokes it with the argument that you put on the left. Again, we haven't listed any types here. The compiler has inferred them all for us, and it's also auto-generalized it for us as well. So you can see in the type signature, we've got the apostrophe A, apostrophe B. That's basically how F# denotes generics. So what does this operator actually allow us to do? What it lets us do is reorder a function invocation expression and put the last parameter first, right? So you might remember from the previous slide, we had that add function, we're passing 2 and 1 to it, right? So what we're going to do now is we're going to move that last parameter, we're going to move it first in the expression. So how does that work? Well, what we do first is we partially apply that add function, right? So we only pass the first parameter to it, and that gives us back a function which takes the second parameter. We then invoke that parameter using that operator, and that operator will invoke it with the thing on the left, which is that 1, right? And then we get back the value of 3. So now you're probably wondering, okay, this is all this weird, crazy stuff, and why do I actually care about any of it? So what this allows you to do is compose together functions into a pipeline that processes data. So you've probably done pipelining on the command line before if you use PowerShell or Bash or Batch. I'm sure everyone's done it at some point. You know, you'll, for example, read the contents of a file. You'll pipe it into grep, and you'll search for some text, and then you'll pipe that out into another file. Now you can do that with that same level of expressiveness and composability. You can do that in F#. So the example on the slide basically composes functions together. It takes a list of numbers, filters out all the odd numbers, converts each number to its English word form, and then takes all those English words and combines them into a single string that's comma separated. So let's step through how that works. The first thing we do is that we open the Humanizer namespace. Now, Humanizer is an open source library that does the integer to English word conversion. What we then do is we create an F# list that contains the numbers 1 to 15. So that 1.15 is the syntax for a sequence expression. So that's going to generate for us numbers 1 to 15. And because we've got it in the square brackets, they're going to get put inside an F# list for us. We're then going to partially apply the seek.filter function. Now, seek.filter is like LINQ where. So remember that seek is short for sequence, and sequence is basically an alias for INumerable. So that's just like LINQ where. So what it's going to do is filter out all of the odd numbers. So the filter function takes 2 arguments. It takes first the lambda that you're going to do the filter with, the predicate, and then it takes the actual sequence to filter. Now, we haven't passed that. We've only passed just the lambda, which means that we've partially applied that function. But that's all right, because then we're going to invoke that function using the pipeline operator. So we're going to invoke it and push in that list of numbers. So you can start to see that clear data flow here. We're starting with that list of numbers. We pipe it into seek filter, and then the output of filter gets piped into map. Now, map is like select in LINQ, right? So what that's going to do is for each integer that it gets off that sequence, it's going to convert it to its English word form using Humanizer, right? So that fun syntax is F# lambdas. They're pretty close to C# lambdas. Nothing too surprising there. So then we take the output of map and we feed it into reduce. Now, reduce is like LINQ aggregate. So what it does is it takes a sequence of something and reduces it down to one of those things. So the typical example is you have some sequence of numbers and you add them all together and you get back the one number. So in this case, we have a sequence of strings, all the English words, and we're going to reduce them down to a single string. And how we do that reduction is with the function that we pass it. So what we've passed it here is the partial application of the sprintf function. Now, sprintf is like string format in .NET. So except that it's more powerful in F# because it's type checked by the compiler. So in this case, you can see in that format string, we've got %s. Those placeholders tell the F# compiler to expect 2 strings to be passed after that function. Now, we haven't passed those 2 strings at all, which means that we've partially applied it. So we've got back from that a function which takes those 2 strings, which is exactly what seek.reduce requires, right? So we pass that partial application to seek.reduce, and it uses it to basically smash each of those strings down into a single string, which is what you can see out on the bottom of the slide, right? So you probably noticed the MapReduce functions there. You shouldn't be surprised to see MapReduce here. MapReduce is kind of has its origins in functional programming, so we shouldn't be too surprised to see it here. So when we look at that, we can straight away see how clean and nice that code is, right? There are no side effects in this code at all. We've composed all these smaller functions together into a larger whole, and the data flow is very obvious. We can see how the list gets piped into filter, and the output of that gets piped into map, and the output of that gets piped into reduce, and then ultimately the result goes into even numbers as words. So you can do a similar thing in C# if you use extension methods and you try and do like a Fluent API, but it's much more difficult to do that in C#. In F#, it's absolutely trivial to write functions that participate in this clean pipelining syntax, because all you have to do is put the input to the function as the last parameter, which basically means they can omit it, partially apply you, and then pipe it in from the front. So here's a real-world example of function composition. This is taken from the F# Azure Libraries integration tests. and it's used to insert a sequence of records into Azure table storage in parallel at up to 4 batches at a time. So straight away we can see a clear flow of data here. We basically have some sequence of items, and then for each of those we're invoking the insert function. So that's going to wrap that item into an insert operation. We're going to take those insert operations and feed them into auto batch. So auto batch is going to take them and batch them up into groups of 100, so that we don't hit table storage with like 100 requests. We hit it with 1 request with 100 things in it. We then take each of those batches and we give it to in table as batch async. And what that's going to do is produce the asynchronous HTTP request to actually send that off to table storage. We're then going to take all of those async HTTP requests and feed them into parallel by degree. And what that's going to do is arrange those things to execute in parallel, but only 4 at a time, because if we have 100 batches, we don't want to do a simultaneous 100 requests to table storage. We just want to do 4 at a time. Then we basically take that parallel arranged work and we feed it into run synchronously. And what that's going to do is it's actually going to cause it to execute and then wait until it's all done and give us back all the results. So once we've got all the results, we push them through seek.concat so we get them out into a single long sequence. So we've expressed an incredible amount of work here in a few short lines that read very, very, very easily. This is the power that function composition using partial application functions and that forward pipe operator gives you. The other thing to note here is that we haven't specified any types. The type inference engine has figured it out all for us. So that function, you can see the type signature in gray, something that takes a string, so that's a table name, takes a sequence of some generic A, so it's auto-generalized it, so items is that sequence of A, and then returns a sequence of some operation result. So if we take a look at the equivalent C# code, we can straight away see how much less readable that is. If you look closely, which you probably can't, that you'll see that I've actually used some LINQ in there, so skip and take and select many. Now LINQ is functional programming, so you can imagine how much worse this code would look if I eschewed all functional programming altogether and just wrote imperative code. It would be much worse than even that. So let's have a look at another F# type of type. Tuples are a useful way of returning 2 or more things from a function. So in C#, if we wanted to do that, we typically use, say, 2 out parameters, or we'd create a class with two properties on it, and then create an instance of that, assign it, and return it. But both of those approaches are quite verbose when all you want to do is just return 2 things. Like, how hard should that be, really? So the tuple type exists in .NET, but it's pretty useless in C# because the compiler doesn't really have any innate understanding of it. And that's very much unlike F#, where the compiler very much understands what a tuple is, and the libraries use it extensively. So in F#, to create a tuple, all we have to do is use comma. So here we've got 2 strings, first string and second string, and we're tupleizing them together using that comma operator into 2 strings. So in the gray, you can see the type for that. It's string star string. That's the F# shorthand for tupleizing 2 types together. So if we were to view that through a C# lens, that would read as like tuple generic string comma string, right? But because they're used so much in F#, it's nice to have that nice shorthand. I believe there's some mathematical foundation for it as well, but we don't need to care about that. So if we want to decompose a tuple, it's just as easy. All we do is we use that comma operator on the left side of a let binding. So here we're taking that 2 strings and decomposing it into first string and second string. Here's a more complex example. Imagine we have some sequence of types, and then for each of those, we're going to create a tuple out of it. So we're saying the tuple has the first element where it's the name of the type, and the second element is the number of properties in the type. We're then going to feed those tuples into the filter function. And you can see there what we've done is we've decomposed that tuple in line in the arguments to that lambda, right? We didn't have to do a separate let binding for that. We could just do it straight in line there. So this is just one way that F# makes it really easy to use tuples. So we've decomposed that into its constituent elements. We've done a filter on the count, and then we've taken whatever's left over from that filter, and we've pushed it into map of seek. So map of seek is a library function, and what it will do is basically create an immutable map, so like a dictionary, based on the tuples we pass in. So it expects a tuple with 2 elements, where the first will be the thing that it uses as the key, and the second is the thing that it uses as the value. So what we're effectively getting here is a map or a dictionary where the key is the name of the type and the value is the number of properties. And you can see how nice and clean tuples make it just to move two things around together. Of course, it doesn't have to be limited to 2. You could do 3, 4, but typically 2 is pretty good. So the next type of type we'll look at is discriminated unions. So discriminated unions are really great when you want to represent a choice between different things. So in C# to do that, we might use a class hierarchy, but in F# it's often better to use discriminated unions, particularly for small hierarchies. So for example, we could model a choice between different contact details. So here we've basically defined our contact detail discriminated union, and we've listed the 3 cases here. We've got phone number, email address, and Twitter. And for each of those, we can bring along a bit of data with them. So for phone number, we've brought along the area code and the phone number string. And for email, we've brought along just the email string. And for Twitter, we've just brought along the Twitter handle string. So to create instances of a discriminated union, all we do is we just use that case label and then pass whatever data it requires. So here in that second section, what we're doing is we're creating a list of contact details, because that's that square brackets, right? And inside that list, we're creating 2 discriminated union instances, the first being my Twitter handle and the second being my email address. Now, at runtime, we need some way of figuring out which type we have on hand. So to do that, we use a match expression. So here we've basically done a loop. We're looped over each of the contact details, and we've gone match contact detail with, and then we've listed the types we want to match against. So we've matched against phone number, we've matched against email address. And you can see that we've decomposed that tuple in line there for us. And in each of the cases, we've printed out something different. Now, the astute among you may have noticed that we missed out the Twitter case here. In F#, this is where we start to see the benefits of static typing coming in. The compiler will give us a warning and tell us that we've actually got incomplete matches on this pattern match, so that it'll tell us that, oh, you've missed out the Twitter case, which is very good because it helps us catch those bugs in our code before we even run them. It's also useful when you're extending and adding to the code or refactoring it. So if I went to add an additional address case to that discriminated union, and what I'd find is that across the code and where I've done all these match expressions, I'd start getting warnings saying, oh, you haven't handled address here and here and here. So it makes it much easier for me to go and find all those places, which I now need to go add handling logic for the new type. So null references are kind of a total pain in the ass. Tony Hoare, the guy who invented them, basically called them his $1 billion mistake, and it wouldn't surprise me if it's cost the industry more than $1 billion. So nulls suck because they're forced on us as developers, right? Every reference that we have can be null at any time, and the only thing we can do is basically protect ourselves from them at the beginning of methods. So you've probably written a lot of plumbing code where it goes, oh, if this parameter is null, then throw argument null exception. And it's like, there's all this plumbing code, I don't want to write it. So in F#, the problem's been solved. What F# does is basically say, well, types can't be null by default, end of story. So here's the example. If I have a game let binding and I try and assign null to it, the compiler just gives me an error straight away. So that colon game syntax there is me forcing the type onto it. So I can't let the type inference engine do it for me here because it's not going to infer the game type for me because that's not a valid value, right? So in order to demonstrate it, I force the type and I try and assign null, and it goes, yeah, no, you can't even do that. Now, the concept of nullability isn't all bad, right? What it's typically used for, correctly, is to represent the presence of a value or the absence of a value, which is obviously something that's useful. So we still want that. So in F#, what you do is you opt into it. It's not forced down your throat. You don't basically have to deal with it all the time. When you want it, when you want to model that in your data models, you opt into it. And the way you do that is you use the option discriminated union. So what the option type is, and it's built in, what it is a description of 2 choices. You've got the presence of a value, so sum of t, some generic t, or the absence of a value, so none. So to use the option type, all we have to do is match against something. So here we're basically matching against my game, which is a parameter to that print game function. And we're basically matching some, and then we print out the name of the game, or against none, and we print out no game. So we haven't had to specify any types here. They've all been inferred for us. So the type inference engine has figured out that my game is option of game, because first we matched against some and none, so it knows it's an option type. And then we've gone g.name, so it knows that we're talking about the name. It knows we're talking about the game type. If we omit some or none from that match expression, we're going to get a compiler warning. So, you've probably seen places in the code where it goes, oh, if you're using resharp, it'll give you a warning saying, oh, you're going to get a null reference exception here. You have the potential. Well, you kind of get that built in because you do a match expression, you get told if you miss out one of the branches. So we will probably have places in our code where we've copied and pasted the same conditional structure around. So I've seen a number of ways people try and do this. What they'll tend to do is extract out, say, the complex Boolean expressions in each of the branches and put them into methods so that they can reuse them elsewhere. Or they might try and model that if thing inside like a class hierarchy. Or they might create a method which takes a number of funcs, and then which func it calls depends upon which branch the code goes down inside the method. They're all kind of awkward. In F#, we've got a particular type for that, so it's called an active pattern. And what it lets you do is isolate and reuse conditional logic very easily. So active patterns make your code more readable, reusable, and composable. And because they let you extract out that conditional logic separately, it also makes the code more testable because you can test that conditional stuff separately. So in the example on the slide, what we're going to do is create an active pattern that takes a phone number and then figures out whether it's a Victorian number, a New South Wales number, or a mobile number. And it does that by inspecting the first two characters in the string. So you can see those three cases, Victorian number, New South Wales number, and mobile number, listed in between the pipes up on the first line. And then we take in a string as a parameter. We match against the first two characters against it. We say if it's 03, then it's a Victorian number. If it's 02, it's a New South Wales number. If it's 04, it's a mobile number. And if it's one of the other ones, then the slide's not big enough, so I just throw an exception. So to use an active pattern, it's pretty much like using a discriminated union. All you do is you just use a match expression. So all we're doing here is we take our number and then we match against it. So we list out the different cases that it could be. A mobile number, a Victorian number, or a New South Wales number, and print out something different in each of the cases. Now, just like discriminated unions, if you miss out one of those, you get a warning from the compiler. So static typing pays you the dividends and makes sure that your code's correct before you even run it. So we've seen a few uses of match expressions now, but we've kind of been missing the big picture about them. In F#, match expressions are more than just simple or complex switch statements, because we can combine them with pattern matching to express powerful conditional constructs. So we'll start with some simple examples and then we'll get a bit more complicated. So we've already seen what it's like to match against literals. So here we're basically taking some string, and if the string is A, then we print out something. If it's B, we print out something. Or if it's underscore. Now, underscore is basically like wildcard. So here we're saying if it doesn't match A or B, then it'll match that third case. We can use pattern matching to decompose F# lists. And this is quite cool. So in this example, we're matching against some list of things, and we're saying, okay, we're going to bind in that first match case, we're going to bind the first element in the list to the name to the name first, and then whatever's left in the list gets bound to the name rest. And then so that case will cover lists that have one element in it, and it will also cover lists that have more than one element in it. So, 2, 3, etc. For lists that are empty, that's not going to match. So we need to cover that case, and we cover it in that second match statement. So here we're basically matching against the empty list. So that makes sure we cover all the cases there. So we've seen tuple decomposition before, but what I didn't tell you at the time is tuple decomposition is actually part of pattern matching. So we shouldn't be surprised to see it in a match expression. And the same applies for discriminated unions and active patterns. They're all part of the pattern matching functionality. Now, again, because F# is statically typed, if we miss out anything in our match expressions, if we have any holes in our conditions, we get a warning from the compiler that tells us you have a hole, you need to cover it. And in a lot of cases, it'll actually tell you the hole that you've missed, and you can just add it in yourself. So far, that's kind of still looked like a fancy switch statement. So what is it really that makes pattern matching so powerful? Well, all of the pattern matches we've seen so far can be combined together and then matched deeply into a data structure. So let's start again with a small sample and then go to a more complex one. So here we're basically decomposing a tuple, but at the same time we're saying in the first case, the first element of the tuple must be true, like the value of true, and the second element, I don't care what it is, but bind it to the name x, and then we print out something. Then in the second case, we're decomposing the tuple, and we're saying, okay, the first element must be the value of false, and the second element is I don't care what it is, just bind it to the name x, and then we print out something. Let's go more complicated. Imagine a function called try_parse_name that takes some string, goes and figures out what the names are inside that string, and if it finds them, it returns some list of strings. So using that option type, or if there's a parse error, then it just returns none rather than some. So the first match we're doing here, we're matching against sum, but then we're matching into sum, and we're saying, okay, the sum has to have a list in it, and that list has to have 2 elements in it. And that list, the first element, has to be the string Daniel. And the second element, I don't care what it is, but bind it to the name last. And if it matches that form, a sum that has a list that has 2 elements in it, where the first is Daniel, then we match and we print out Daniel with surname and then the last name. In the second match case, we're doing a similar thing, except this time we're matching against a list with 3 things in it. So again, the list has to start with Daniel, but then the second 2 names, middle and last, can be anything, and whatever they are, they get bound to the names middle and last. In this third case, we're going to match against any list that starts with Daniel. Now, match expressions are evaluated in order, so this won't match lists of length 2 and 3 that start with Daniel, but it will match lists that only have Daniel in it, and they will match lists that start with Daniel and then have 4, 5, 6, etc. elements in it. And whatever those other items are will get put into the other names for us. Now we also want to cover the case where we have a list, but it doesn't start with Daniel, and that one will cover it, so that entire list will get bound to the names. And then finally, we need to make sure we've covered all the pattern matching cases here. Because we've matched against some, we also need to match against none. So you can see there that pattern matching is an extremely powerful construct that allows you to tersely express conditional matches against data structures and then inside them. Awesome. Now let's go more complicated again. So this is a real-world example of pattern matching, and this is taken from that F# as dual library, and it's part of the code that implements a LINQ-style expression tree parser that lets you write statically typed where queries against table storage. So just like we write iQueryable queries against databases, and we have things like Entity Framework that reads that expression tree and then generates SQL for us, this bit of code, or at least a bit more than this, but that's part of it, does a similar thing on F# expressions and then produces a table storage query. So this code is an active pattern that takes an expression and figures out whether that particular expression is a conditional comparison operation. So in this case, let's zoom in because it's a little bit complicated. We've got this first match, and what it's doing is it's searching that expression for and matching against whether it's a function call. And if it's a function call, it has to be the equals function. So the equals function is an operator, so it is just a function. And we're doing that by using the specific call active pattern. Now that's part of the F# libraries, but what it's basically going to do is if the expression is a function call and the function call is at the equals, then it matches. And it comes along with a bit of extra information. So the first 2 pieces of that information, I don't care what they are, so they just get underscored away. But the third piece of information is the list of parameters that are passed to the function. Now this is a binary operator, which means that it takes 2 arguments. So what I've done here is I've matched against the two things in the list, where the first thing will be called left and the second thing will be called right. And if we match all of that, then we're basically saying that yes, this expression we have on hand is a comparison operation. It's an equals comparison operation, and here are the left and the right expressions on the left and the right of the equals operator. So if we zoom back out on that now, we can see what this is trying to do. What it's doing is identifying equals, greater than or equals, less than or equals, less than, and not equals. And of course, if it's something else other than a comparison operation, then that's the underscore on the last case, and then we say no, it's not a comparison operation, and we just return none. So this sort of powerful pattern matching means that in just 100 lines of code, F# Azure can implement a whole LINQ style provider for table storage. Like you couldn't even attempt to do something in that little amount of code in C#. So that the power that active patterns matched with this pattern matching stuff, what that gives you is just really insane. Seal of approval. So now let's have a look at how we do async in F#. So C# relatively recently gained the ability to write async await style code, and those of you who have used it would know how much cleaner it makes your async code and how much easier it is to read and easier it is to test and easier it is to maintain, right? What most people don't know is that F# actually did it first back in 2007. So the example up on the slide is an async computation expression, and what it does is it asynchronously queries table storage using F# Azure and finds the first game in the game table where the developer is 343 Industries. So you can see this equals comparison that's happening there. That is an example of what we matched in the previous on that previous slide, right? So we've got the left, we've got the equals, and then we've got the thing on the right. So let's break it down. So the first thing we're looking at there is your async curly brace. Now that defines the extent of the async computation expression. Then inside that, what we're going to do is we're going to do that query against table storage, saying we're starting with all the games, we're filtering out based on the developer, and we're querying from the game table. Now that weird less than ampersand greater than thing is how you define an F# quotation. So that's how you instruct the compiler to generate an expression tree. So it's just similar to the way C# you use expression and it generates an expression tree rather than actual code. It's a similar construct in F#. It's a bit more powerful though because you can do more with it. So what we're doing here is we're doing that query and we're using let bang instead of normal let, right? And what that's doing is basically an await. So it's very similar to how await works in C#. So when that query finishes asynchronously, we get the results back bound to the named games, and then the rest of this computation expression continues executing. So we're going to loop over those games. We print out the names of them to the console. So the other thing to note here is we've taken that async computation expression and we've piped it into async run synchronously. Now this is one place where async is different to C#'s async. In C#, when you call an async method, it starts executing immediately and then returns. Whereas in F#, when you evaluate an async computation expression, it doesn't execute. It waits for you to kick it off. So it allows you to prepare work, arrange it, and then execute it. So in this case, we've basically created our async expression, and then we've actually caused it to execute synchronously and get the result back. So the async computation expression is just one type of computation expression in F#. Another type is the seek or sequence computation expression. And what this lets you do is generate a sequence of items. So you might recognize this as similar to yield return in C#. So the code up on the slide basically re-implements a LINQ style where function. So it takes two things, the predicate, which is the function which is going to test each item in the element to see whether it matches, and obviously the sequence to filter. And because I put that sequence parameter last, I can use this in a pipe because I can emit it and then pipe things in, right? So the seek curly braces is the extent of our sequence computation expression. And then we're going to loop over that sequence and test each item in the sequence against the predicate. And if it matches, then we yield it. Again, we haven't specified any types here, and it's all been inferred for us by the compiler, which is pretty cool. So F# and its computation expressions, they really do show off the elegance and the power that the language has. Both async and seek are actually very similar constructs under the covers. So what F# does is it implements this computation expression thing in the compiler, and then seek and async are actually things that are implemented in its libraries. This means you can write your own computation expressions, but that's kind of a topic for a whole other talk, so I won't go into it. C# in comparison hard codes its implementation of yield return and async into the compiler. If you decompile what it generates, there's actually quite a lot of similarities between the way yield return and async works. but they're both different and they're closed into the compiler. In F#, computation expressions are generic and they're open for extension. So type providers are components that extend the F# compiler and introduce static types to things that are outside of F#. So, for example, you can think about a type provider that provides static types for things like regular expressions, XML, JSON, or even SQL. Type providers help us eliminate magic strings from our code, because what we could do, for example, is if we have a regular expression, if we change that regular expression, the type provider can make sure that the code that we write against the regex continues to work because it's providing static types for that regex. So the best way to demonstrate this is in Visual Studio. So I'm just switch over to that. All right, so we're in Visual Studio now. And the first thing to notice is that what we're using here is an F# script file. So in C#, typically we'll have source files and we'll build them into an assembly. Now you'll do that in F# too. You'll still have your F# source files and you build them into an assembly. However, in F# you do have the option of writing a script file instead. So for those of you who have used LINQPad, you know how useful it is to just be able to go off and write a quick bit of script and find out whether something works or not, and just test it out, right? Without having the overhead of a project and all that sort of stuff. Well, F# has that built in. This is an F# script file, and you can evaluate the F# script file in the F# interactive. So that's that second pane here over on the right. So the F# interactive, there's obviously one embedded into Visual Studio, but it's also a command line executable you can use. So let's have a look at what's in the script file here. So the first thing we've got here is this #r construct. So the #r is basically a scripting construct that will load this assembly for us. And the assembly is the thing that contains a type provider in this case. So on this second line, what we're going to do is we're going to create the phone regex type, which will be provided by this F#x regex type provider. And we're going to pass that type provider this regular expression. Now this regex is basically going to take a phone number and parse out the area code and the phone number into those two named groups, right? Then what we're going to do is define a parse and print number function. Now this function takes a string, shoves it through that phone regex, and gets the match back from it. And if the match was successful, we then print out the resulting area code and the resulting number. So you can see here that the match result has come back with statically typed properties. So that result.area has worked out with a property there, and if we go dot, you can see that it shows up in IntelliSense as well, which is pretty nice. So if I now go change that particular regex, so let's say here I take this area and I change it to say area 57, straight away we can see we get a compile error. So this is again F# static typing paying us dividends and making sure that the code that we write works before we even run it. So it's detected that that named group doesn't exist anymore, so we haven't got that property and we get a compile error. So that's very useful. So if I actually now run this code, select it and execute in interactive, we can see that this final line here where we're taking a number and pushing it through parse and print number works just fine, and we've printed out the area code here and the phone number. So let's look at another type provider. What we've got here is another script file for a SQL client type provider. Now what we're doing here is we're using this piece of SQL, and what that's going to do is going to query the AdventureWorks database and pull out the customers who have spent the most with us. So in this case, we've got this two named parameters that are passed to this piece of SQL. So we've got top N, and we've got a filter orders more than. What we're going to do then is define this top customer query type provided by the SQL command provider, to which we pass that piece of SQL. We then create an instance of that particular query. And then in an async computation block, what we're going to do is asynchronously execute that against the database and pass in those two named parameters. You can see that they've come through as proper named parameters, they have names, and they've also come through properly typed. So if we hover over this and look at the type of this parameter, we can see that it's come in as a int64, which is correct. And if we look at orders more than, it's a similar story there. It comes through as a decimal, which is also correct. So once we've got those results back asynchronously, what we're going to do is loop over them and print them out to the console. So again, you can see these result types that have come back have been provided by that type provider, and we've got proper properties for first name, last name, total due, and those have come from the columns that we've selected in our SQL up here. So that's pretty cool. Now, if I go and change this piece of SQL, let's say I change top end to just top, we straight away get an error in our code, our compile error, saying, oh, the top end that we're using down here doesn't apply anymore because our SQL's changed. So that's very, very handy. So we know as soon as we change our SQL, we know whether the code that's using the SQL is still compatible. But it's not just testing your F# code. If I go and change here, say change last name to surname, and surname is not a column in that table, we'll still get a compile error, and it will tell us that the SQL that we've written isn't actually valid. If we look here, we can see that error. So what this means is that we can write raw SQL in our code for when we need those performance-tuned queries, and we don't need to run our integration tests every time we make a change to the database schema to see whether we've broken any of that SQL. All we need to do is compile the project, and it will tell us if our SQL is valid or not. So that's incredibly handy and incredibly powerful. So if I run this code now in the interactive, we should see that we've pulled those top 5 customers and printed out their amounts here. So that's pretty cool. Now, while I'm in Visual Studio, I'm going to take the opportunity and show you what an F# web project looks like. Now, I'm not going to spend a lot of time on this because, to be honest, they're not particularly different from our typical C# web project. So it's something pretty much anyone who's worked with web, particularly MVC, before would be familiar with. So here you can see, if we zoom in on it, we've got our very typical set of folders that we expect to see, like controllers and views, and even our global ASAX file, right? So if I open that global ASAX file, the code that we have there is pretty much typical of what we'd expect to see in a web application. So we've got our global class, which inherits from HTTP application. If we scroll down, we've got the our expected application start method, which does all the things that we expect it to do, like registering areas and registering routes. If we look at the route registering code here, this is again what we expect to see, and this is pretty much exactly like it would be in C#. We're defining those routes, that the default one, which takes the controller and the action and the ID. So all very standard stuff. So now if we go take a look at the dumbest and simplest controller possible to have in this home controller, what we've got here is basically your action method that returns the view for index. So if we look at the view for that, we can see that they're just razor views. So this is index CSHTML. Now, unfortunately, there's no such thing as an FSHTML. Razor only supports C# and VB, which basically means it really only supports C# because no one cares about VB. But unfortunately, there isn't F# support for that. But it's not a big deal because you don't typically do a lot of crazy logic, or you shouldn't be doing a lot of crazy logic in your views anyway. And Razor does the job just fine. So if we have a look at a slightly more complex controller, we've got the games controller, so it's obviously not really that much more complicated, but it does do something this time. And what we've got here is basically an asynchronous action method. So what we're doing is we're asynchronously querying table storage, pulling a list of games, and then giving it to the index view. Now, async is not the same as TPL tasks, so an MVC expects TPL task for its async action method. So what we're doing here is we're kicking off that task as a TPL task, which means that the type returned by our action method is basically what MVC would expect, something that returns, in this case, a task of view result. The view for this is again quite straightforward. If we look at what that is, it's something that takes a list of games. So those are record types, but it's all .NET, right? So that's consumable quite fine from C#. In this case, there is C# Razor. So this is going to take that list of games, and we're going to loop over them and print them out into a table. Now, if I run this and show you what it looks like in the browser, you shouldn't be surprised. we've got a very boring, just basic template homepage. And then if I go into the games page, we can see that we've hit table storage and we've pulled a bunch of games and put them into that table. So that's all nice and good. So now I'm going to switch back to the presentation and we'll finish up. So we just saw a small example of what an F# web project looks like. Now, it's very similar to C#. After all, F# is just a .NET language, so everything we do in C# we can do in F#. However, the out-of-the-box tooling for doing ASP.NET with F# is non-existent. So unfortunately, at this point in time, you do actually have to go grab a couple of Visual Studio extensions. So you need to grab F# MVC5 and F# Web Item templates. And that'll allow you to basically go new project and create an F# web project, which is great. The other thing that you'll need to think about is grabbing the F# Power Tools extension. So the F# Power Tools extension will give you resharperish abilities in the editor. So you'll get things like renaming and find references and unused let bindings, for example. Unfortunately, ReSharper itself doesn't support F#, but Visual F# Power Tool does give you back some of those things. And it's an open source project, which is pretty cool. So the guys working on it have actually been moving at quite a fast pace and have added a lot of features in just this year alone. Now, the tooling is a bit flaky for an F# web project. For example, it doesn't quite handle folders particularly well. Sometimes it freaks out a little bit and you have to tweak the file by hand. So what some people choose to do instead is use a C# web project as a hosting project instead. So when you do this, you can pretty much decide where you want to draw the line here. You could write C# controllers and then just write all the rest of your code in F# and just call it. Or you could choose to do everything F# and just use the web project as a hosting project. Now, how you want to do that is up to you. So, in conclusion, I've shown off a whole bunch of F# language features that help us with those programming problems that I mentioned at the start. So composability, reliability, maintainability, readability, reliability, testability, concurrency. What I like about F# is the language is made up of these little building blocks that all come together to help you write programs that are more composable and readable. So for example, purity and immutability allows us to write more easily concurrent applications. Things like partial application of functions and pipelining mean that our code is much more readable and therefore much more maintainable, and we're composing things together, so it's much more composable and reusable. And things like active patterns mean that we can extract out that conditional logic and test it separately, so our code is more testable. So now that you've seen some F# and you've seen how clean and terse it is and basically how awesome it is, right? You'll probably want to go off and find out some more about it, because I don't expect that after having just seen some syntax for an hour, you're now F# experts in the language. So you'll probably want to go off first to try fsharp.org, and they have some basically tutorials there to teach you the basics F# syntax. And the great part about that site is that you can actually type into an editor in the browser, and it will go off and compile and evaluate that F# that you write and give you back the result in the browser, which is very, very cool. Another site that I highly recommend is fsharpforfunandprofit.com. So the guy who writes that site, Scott Lashian, he writes incredibly good articles that talk about functional programming concepts as well as concepts in F#. Now, he is very strong on the fact that you don't need a crazy math background to understand functional programming. So all the articles that he writes are targeted at .NET developers who don't have that crazy math background, which you don't need to understand functional programming. So he explains things very clearly and very simply. So that's a really excellent resource, and I highly recommend you check it out. There's also fsharp.org, which is sort of the community hub site for F#, because F# is open source, the compiler is open source, and was way before VB and C# became open source. And there's also, now that the F# Visual Studio extension, like the F# tooling, is open source, so that's also sort of based around there as well. So fsharp.org has some guides, and it has videos, and it has a lot of links to popular F# libraries that you might want to use. So it's a good place to go and just see out, find links to things.